The next topic we'll cover in ECE 111 is energy conversion. Energy conversion is a required course for electrical engineers, an optional course for computer engineers. What we cover in 331 energy conversion is AC motors, DC motors, transformers, and various topics like that. For today's lecture, we want to just look at one of the topics covered in 331, specifically operation of transformers and how our power grid works. So the specific topics would be transformer operation, the efficiency of the AC power grid, why we use AC rather than DC in our power grid, and how come there's transformers and substations all across North Dakota. Now to start with, magnetism and current are inherently related. If you have current flowing through a wire, that produces a magnetic field. From Faraday's law, if I have a changing magnetic field, that produces a voltage proportional to the number of turns. Those two together allow you to have transformers. If I take a wire and wrap it around an iron core, that produces magnetic flux. The units of magnetic flux are in amp turns. The magnetic flux is sort of like current. It flows through a conductor, in this case iron, in a closed path. If I have a second coil of wires around the same transformer, the same flux that goes through turn 1 also goes through turn 2. By doing so, I can take a voltage on the first side and induce voltage on the second side. Now the equations for how transformers work is thus. The flux that I create in the first winding is proportional to the number of turns times the current, and the units are amp turns. Iron is a very good conductor of magnetic fields, about 8,000 times better than air, so almost all magnetic flux will flow through the second coil. From conservation of flux, I'll have the flux in 1 is flux in 2, meaning N1I1 is N2I2. Doing some algebra, that means that the current on the secondary side is related to the turn ratio times the current on the primary side. You also have to have conservation of energy. The energy in is volts times amps. That has to match the energy out, also volts times amps. Doing a little bit of algebra, that says the voltage on the secondary side is proportional to the number of turns on the secondary side divided by the number of turns on the primary side times the first voltage. So transformers convert one voltage to another. With a transformer, I can convert 120 volts to 3000 volts, or whatever you want, just by the turn ratio. That only works, however, from Faraday's law if there's a change in magnetic field, meaning the current's time varying. Hence, transformers only work at AC. They don't work at DC. A nice effect of transformers is you can also change impedances with a transformer. If I apply a voltage on the primary side on N1, I'll get a voltage on the secondary side. Apply a current on the primary side, I'll get a current on the secondary side. Voltage over current is impedance. So if I have an impedance on the secondary side, it looks like a different impedance on the primary side. And it turns out that the impedance seen on the primary side is related to the turn ratio squared. It's where you're going to divided by where you're coming from squared. What that means is I can change the impedance. One of the applications is this. If you've ever seen one of your parents' or grandparents' stereos and it's a big, heavy stereo that weighs a ton, it probably has a transformer in it. The problem they're trying to solve is this. If I have a vacuum tube amplifier or a transistor amplifier, it typically has a fairly high output impedance. If I take the circuit and try to drive an 8 ohm speaker directly, almost all the energy is lost in the 100 ohms impedance inside the amplifier. This is a stereo, which is a whopping 7% efficient. 7% is not very good. I can fix that by using a transformer, and this is where it adds weight to your stereo. Transformers inherently have iron in them. The iron makes it very heavy. What the transformer does is I can take the 8 ohm speaker, going through a transformer, it now looks like 8 times the turn ratio squared, and now looks like an 800 ohm speaker relative to the amplifier. I can drive an 800 ohm speaker at right around 89% efficiency for this circuit. Thus, by using a transformer, I went from 7% efficient to 89% efficient, just with a 10 to 1 ratio transformer. A sidelight, however, is that by doing so, I've also made the voltage 10 times higher. To have 10 volts at the speaker, which is 12 watts, I need to have 100 volts inside the stereo. What that means is if you ever see a stereo that's extremely heavy, meaning it has transformers inside of it, don't stick your hands inside of it. You're probably dealing with hundreds or thousands of volts inside the transformer to drive your 8-ohm speaker. So this one uses transformers. Another use is in the power grid. Before we analyze the power grid, though, I want to look at how to model a transformer. This is one of the homework assignments. Given some measurements, come up with the models for the transformer. Now, a transformer has two parts. It's got the turn ratio. That's the part I really care about. In addition, there's these line losses. The transformer is inherently made out of copper wire. A long strand of copper produces an inductance and resistance. In addition, I've got an iron core. The iron core will dissipate energy. So if I power up the transformer, it's going to get warm. That's modeled with the core losses, R sub C. It also has some inductance. Again, a transformer is a coil around an iron core that inherently produces an inductor. To model a transformer, I want to find out what's the core losses, that's the energy that's dissipated just by powering up the transformer, and the line losses. As I use the transformer to start drawing current, the losses go up. To do that, we need to know a thing called power factor. Power factor is related to the inductance and resistance in the circuit. Power factor is the real power, the power through the resistor, over the magnitude of the voltage times magnitude of current. It's also, if I have a complex impedance, it's the cosine of the angle of the complex impedance. If I want to measure the actual power produced by a circuit, the actual power is the magnitude of the voltage squared over the impedance times power factor, or the magnitude of voltage times magnitude of current times power factor. With the measured voltage, power factor, and power, I can sit there and tell you what the impedance is. It'll be from this equation. So, a typical test on a transformer looks like this. I'll do two tests. One test to measure the line impedances, and a second one to measure the core. The open circuit test measures the core. What you do is you leave the secondary side open, apply the rated voltage to the primary side, measure the voltage, current, and power, and that'll tell you the core. The second test is called the short circuit test. On the secondary side, I short the primary side, on the secondary side apply a voltage. It's not the rated voltage because that'll use too much power. Any voltage, something small, works. When I apply a short circuit test, I measure the voltage, power, and power factor, and from that I can compute the line, the R line and X and the impedance line. For example, for the previous data, the open circuit test had a voltage, current, power, voltage, power factor, and power. With that, I can tell you the impedance of the core. That's 678 ohms plus J33,000. The core typically is modeled in parallel. This is the series impedance. To convert that to a parallel model, what I do is I take the inverse. The real part is 1 over R core. The complex part is 1 over JX core. So separating those, it says that the model for the core is 1.68 mega ohm for RC and J33 kilo ohms for the inductance. The short circuit test tells you what the line impedances are. Here I short out the primary side. That shorts out the core, so this no longer matters. Apply test voltage on the secondary side, measure the power and the power factor, and from that I can find the impedance. In this case it's 0.45 plus J.1 ohms. This is the series model, which is what we use for the line. So the line looks like a 0.45 ohm, J.14 ohm inductance. Put that together with the core. Here's the model for the transformer. Now, what transformers are used for is they help move energy over long distances. For example, in 2017, North Dakota produced 41,000 gigawatt hours of electricity. That equates to $415 billion or $1 million. Almost all of that energy is exported out of the state. So energy production is a large industry for North Dakota. For this to work, however, I need to be able to transfer power over large distances. So here's the problem you have. I've got a coal plant in western Dakota. How do I transmit the power 1,000 kilometers to a place like Minneapolis, St. Paul? Edison's idea was to have the DC power grid. The problem with DC is transformers don't work at DC. So if I want the customer to receive 120 volts DC, I need to transmit 120 volts DC. That doesn't work over large distances. For example, if I have a copper wire that's 1 centimeter diameter and 1,000 kilometers long, that copper wire will have a 14 ohm impedance. To transmit 1,000 megawatts, the size of a typical large coal plant, I'll be transmitting 83 megaamps at 120 volts. The line losses, the losses in 14 ohms at 83 megaamps, is 9.9 times 10 to the 16th watts. The efficiency of a DC grid over 1,000 kilometers is the power of the load divided by the total power. For a DC power grid, it's 0.0000001%. Basically, you can't build a DC power grid and transmit power 1,000 kilometers. Edison's idea was to use a DC power grid and have a power station every 2 or 3 miles. Edison lived in New York City, and 2 and 3 miles is a long distance in New York City. That doesn't work real well in North Dakota. Tesla's idea was to, instead of using DC, use AC. With AC, transformers work. What I can do with AC is I can take the 120 volts, bump it up to 345,000 volts at the power plant, transmit the power at 345,000 volts, 1,000 kilometers to Minneapolis. When I get to the edge of town, I bump down the voltage to 13,000 volts at a substation. There I transmit the power to the neighborhoods. I then bump it down again to 120 volts, taking it to your house. And this is the neighborhood substation, or neighborhood transformer, that takes the power to your house. Works at AC, doesn't work at DC. The reason for doing that, and these are the models of the transformers that we had. This is the core losses. The line losses are right here. Another core losses, line losses. Here's the model of the transformers. What I want to do now is analyze this circuit. To do that, what I do is use what we did before. Take everything and convert it to the customer side. When I do that, the impedances change as the turn ratio squared. So these will be multiplied times 120 divided by 13,000 squared. These will be multiplied by 120 over 345,000 squared. So these impedances get much, much smaller. This is what the power grid looks like relative to the customer. Oh, last thing I should mention. The 345,000 volts becomes 120 volts as seen by the customer. Now analyze this circuit. This is just a circuits problem. We've already covered this. I just write the voltage node equations. The voltage of V1 is whatever it takes so that the current's balanced. Current left, down, right, must add to 0. At node 2, the current's left, down, right, add to 0. At node 3, the current left and down add to 0. Write your 3 equations for 3 unknowns. After writing the equations, I can now solve, and I get my voltages. The efficiency is the power to the load divided by the total power. The total power dissipated is the power in all the resistors combined. If I include everything, I have a 26% efficient power grid. Not great, but way better than what Edison had at 0.0000001%. If I ignore the core losses, I'm up to 98% efficient. What that tells me is that I can't afford to build a power grid for a single customer. The efficiency is too small. If I have 1 million customers, however, the core losses get divided up among the 1 million customers, so they essentially don't matter. For 1 million customers, I just care about the line losses. I'm more like 98.2% efficient. That's how our power grid works. We use transformers, and with the transformers, the power grid is actually very efficient. It's right around 98% efficient. That's similar to the last problem on the homework. It's given a slightly different power grid. Calculate the voltages after converting it through the transformers, calculate the losses in each element, and then calculate the efficiency.